Hello there. In this video we're going to discuss a very special and probably one of the more famous sequences of integers, and that is the Fibonacci numbers. So this is the Fibonacci numbers. And it's defined as follows. So the 0th Fibonacci number is 0, the first is 1, and the rest are defined recursively as fn is equal to fn minus 1 plus fn minus 2, and this is going to be true for n greater than or equal to 2 in the set of natural numbers. We're going to discuss a few properties, both geometric and algebraic, for the Fibonacci numbers in this video. Alright, so we're just going to begin by calculating the first few Fibonacci numbers just to get a sort of idea of what's going on with this sequence. So the first two is going to be 0 and 1 by definition, and then all the rest of them are just going to be the sum of the preceding two Fibonaccis. So 0 plus 1 is going to be equal to 1, 1 plus 1 is going to be equal to 2, 1 plus 2 is going to be equal to 3, 3 plus 2, 5, 5 plus 3, 8, 8 plus 5, 13, 13 plus 8, 21, 21 plus 13, 32, and the process is going to continue onwards. Actually, that should be 34, right? No biggie. Alright, so those are the first few Fibonacci numbers, so clearly this is a monotonically increasing sequence of natural numbers, strictly monotonically increasing except for these two numbers here, for which they're equal. Alright, so let's just look into a easy geometric interpretation of this, which begins why a lot of people think this is one of the more beautiful numbers of mathematics. So let's look at the geometry of it. So I'm going to be constructing a sequence of squares. I'm going to be stacking them adjacent to each other, whose dimensions are the Fibonacci number times itself. So I'm going to start off with a 0 by 0 square, which is just a point. So there's my first Fibonacci square, I guess you could call it. And then I'm going to have a 1 by 1 square. So my 1 by 1 square is going to be here. And then I'm going to have another 1 by 1 square next to it. So that's Fibonacci 0, 1, and 2 in terms of squares. Then I'm going to have a 2 by 2 square, and what I'm going to do is I'm going to stack it on top. And then I'm going to have a 3 by 3 square, which I'm going to stack here. And then I'm going to have a 5 by 5 square. And then I'm going to have an 8 by 8 square, which I'm going to put, let's put in green over here. Okay, cool. So as you can see, the Fibonacci numbers, if we put it in terms of squares, they all stack nice and beautifully onto each other. So if you actually connect all these vertices together, let's do this in, say, black. So if I connect that and connect these and sort of connect these little corners, so the next square is going to be somewhere up here, right? So this point is going to sort of loop around here, and you sort of get this little spiral looking thing. In particular, it's a logarithmic spiral, right? Which is typically in polar form something like r is equal to a times e to the b theta, right? Something of this structure, right? I'm not going to go into this proof here, but I'll leave you as an exercise if you're familiar with polar curves on how to sort of guess what this true form is, right? But this spiral is sometimes referred to as the golden spiral. Now you may be wondering, well, why do we use this term golden spiral? Like, why is it not called the Fibonacci spiral? Well, some people do refer to it as this, but another more common name is the golden spiral. Does this Fibonacci sequence have any connection to the golden ratio or the golden angle that we talked about last time, right? So let's bring back just some of the couple basics of the golden ratio, right? So remember that x squared is equal to x plus 1 does have two solutions, right? We have the golden ratio phi, and we also have the silver ratio negative 1 over phi, right? Which some people just abbreviate as phi star. Right, so phi here is the golden ratio, right? So what I'm going to do is I'm going to take this equation, I'm going to multiply both sides by x. So that's going to give us x cubed is going to be equal to x squared plus x. We can do it again and have x to the fourth is equal to x cubed plus x squared. And then we have that x5 is going to be equal to x4 plus x3. So we can, of course, extend this as many times as we want, and we can write this as xn is equal to xn minus 1 plus xn minus 2, right? So we have this equation. So remember the Fibonacci numbers and how they're defined. So they're defined as fn is equal to fn minus 1 plus fn minus 2, where this is, of course, true for n bigger than or equal to 2, and f of 0 is equal to 0, and f of 1 is equal to 1, right? So notice that these two statements do share some similarities with one another, right? So we start to begin to see the connection between Fibonacci and the golden ratio, right? So remember, if phi satisfies this equation, then we're going to get the expression that phi n is equal to phi n minus 1 plus phi n minus 2. And we also get the equation that negative 1 over phi to the n is equal to negative 1 over phi n minus 1 plus negative 1 over phi n minus 2. So both of these are true since they satisfy the original quadratic equation. Alright, so instead of writing this nasty looking negative 1 over phi, I'm just going to call this phi star just for simplicity for the upcoming few minutes. So now what I'm going to do is I'm going to define a new sequence. So I need to somehow build this sequence of powers of phi and sort of connect it with the Fibonacci sequence. So I'm going to define a sequence that sort of represents that. So the sequence that I'm going to define AK to be equal to A times phi to the K plus B times phi star to the K, right? And here A and B are going to be some real numbers. So different real numbers gives you different sequences in terms of powers of phi and its conjugate. Alright, so let's just look at a couple properties of this general sequence, and then we'll figure out what A and B should be in a moment, right? So what is AK minus 1 plus AK minus 2? Let's see if that has any relationship or cute relationship to AK. Alright, so that's going to be equal to A times phi K minus 1 plus B phi star K minus 1, and then plus A phi K minus 2 plus B phi star K minus 2. Let's just rearrange this in terms of those coefficients, right? So in terms of A, and then we're going to do in terms of B. So that's going to be equal to A times phi K minus 1 plus phi, there should be, so that's just K minus 2, and then plus B, so we're going to have phi star K minus 1 plus phi star K minus 2, right? So remember that phi and phi star satisfy the quadratic equations and all multiples of phi and phi star higher than it. So remember that these two expressions are precisely equal to A phi k plus B phi star k, right? And this by definition is just AK, right? So this general sequence that we've defined here, right? So therefore AK is equal to AK minus 1 plus AK minus 2, where AK is equal to A phi k plus B phi star k, right? Where A and B are any real numbers. So no matter what numbers you choose for A and B, this identity always is going to be true. So that's a very nice property for this sequence that we've just created. So let's just mention that right here. So this is true for any real numbers A and B in the reals, right? Which is very cool. All right, so now we're going to just set these the sequence equal to a couple things. So we're going to let So for k is equal to 0 and k is equal to 1. So now we're going to try and construct our Fibonacci sequence. So we want A0 to be equal to F0, and we want A1 to be equal to F1. So that means F0, as we know, is going to be 0, and F1 is going to be 1. So this is what we're going to define as our two initial points. And then we're going to see what values of A and B satisfy that particular expression. Alright, so that means that A0 is going to be equal to, so A0, we're just going to plug in 0 here, so phi 0 and phi star 0 is just going to be 1. So we're just going to have A plus B, and A1 is going to be equal to A phi plus B phi star. And we want A0 to be equal to 0 and A1 to be equal to 1. So if we write this in matrix form, probably is the easiest way to look at it. We're going to have 1, 1, phi, phi star times AB is going to be equal to 0, 1. So let's write this phi star in its standard representation. So that's going to be 1, 1 phi negative 1 over phi. AB is equal to 0, 1. And we're going to solve this matrix equation for AB, right? So I'm going to multiply the second row by phi. So that's going to be equal to 1, 1 phi squared minus 1 times AB is going to be equal to 0, phi. Right? So let's see here. So now I'm going to add row 2 and row 1 together to sort of eliminate the B parameter. So that's going to give us 1, 1 phi squared plus 1, 0. AB, and that's going to give us 0, phi still, since 0 plus phi is phi. So from here we can solve this equation for B, right? So we have that phi squared plus 1 times A plus 0 is going to be equal to phi, right? So that means A must be equal to phi divided by phi squared plus 1, right? So remember that phi squared is the same as phi plus 1, so we can rewrite this as A is equal to phi divided by phi plus 2, right? And this is because phi squared is equal to phi plus 1, a property that we derived previously, right? So through some algebraic manipulations using the definition of phi, where phi is equal to 1 plus the square root of 5 over 2, it's very easy to prove that this phi over phi plus 2 is actually just going to be equal to 1 divided by the square root of 5. A very nice irrational number, right? So using this other equation that we have, so we have 1 over the square root of 5 plus b is equal to 0, right? Because a plus b is equal to 0. So that means that b is equal to just the opposite of a, or negative 1 over the square root of 5. Alright, so now let us bring back our sequence, right? So since ak is equal to ak minus 1 plus ak minus 2, with the sequence starting at 0 and then 1, and the values that make this true with respect to ak are a is equal to 1 over the square root of 5 and b is equal to negative 1 over the square root of 5, right? So these two coefficients make these two statements true, right? So if that is true, then that means AK under these assumptions is equivalent to the Fibonacci sequence FK, which is very, very useful. So that means the Fibonacci sequence FK, or you can use Fn if you want. So this is going to be equal to 1 divided by the square root of 5 times phi to the power of k plus negative 1 over the square root of 5, so that's a and b, times negative 1 over phi to the power of k. So using some simple algebra and combinations of these things, we can just get that this is going to be equal to phi k plus negative phi to the minus k, all divided by the square root of 5. And of course it's minus k because phi is in the denominator of this other expression, right? And that should be a minus sign in the middle, right, because of that guy. Okay, cool. So this is what some people refer to as the generating function for the Fibonacci numbers, because I can say, you know, if k, what is the 10th Fibonacci number, for example? I can say phi 10 is equal to F10, sorry. So the 10th Fibonacci number is going to be equal to phi 10 minus negative phi to the power negative 10 all over the square root of 5. And of course, then you have to calculate powers of phi, which might not be the most prettiest, but you'll get some number out. So at least you can generate them without having to calculate F9, F8, 7, 6, 5, 4, 3, 2, 1, and so on. Now there is a special way to generate powers of phi to an arbitrarily large power, but we'll discuss him in a couple videos from now. But anyway, these are just some basics for the Fibonacci numbers. In the next video, we'll discuss some more properties on the Fibonacci numbers as well. Hope you enjoyed.